Hello, everyone, and welcome to our webinar. Our topic today is titled Frame It Right, Back to Basics for Big Buildings. My name is Karen Beatty, and I will serve as moderator for the session. Our speaker, Darren Graham, and I both work for APA, the Engineered Wood Association. APA is a nonprofit trade association representing manufacturers of a variety of common structural engineered wood products. In addition to quality verification and product testing, APA conducts research to improve engineered wood construction systems and educates users and specifiers on the product's proper use and potential applications. Before we start today's webinar, I need to cover some housekeeping details. Darren's presentation will last about 50 minutes. To ensure that everyone can hear it clearly, we have muted all participants. We do encourage you to submit questions by typing them into the questions pane on the control panel on your screen. We should have time to answer most questions, but if we run short, we'll be sure to post a Q&A summary on our website, along with a recorded version of today's program. We should have those posted in a week or so. I'd also like to note that today's webinar is approved for AIA and ICC continuing education credits. About an hour after the conclusion of the webinar, an email will be sent to each attendee. It will include a link where you can get customized AIA and ICC certificates of completion. Our presenter today is Darren Graham, Engineered Wood Specialist for APA. Based in College Station, Texas, Darren is an engineered wood specialist who has over 18 years of experience with engineered wood products and their applications. Darren started his career with Wood I-Beam Incorporated in Florida, continuing with Georgia Pacific after company ownership transferred to GP. He went on to work for Louisiana Pacific as a district sales manager in several territories in the U.S. and has worked on software development for the industry and as an independent consultant to sales teams. Darren has been recognized for his national sales efforts and also for his work as an instructor in engineered wood products training. For those of you just joining us, welcome to APA's webinar, Frame It Right, Back to Basics for Big Wood Buildings. I will now turn the microphone over to our speaker, Darren Graham.
Thank you, Karen. Today's focus is framing large wood structures using engineered wood products. When we talk about engineered wood products at APA, we're looking at structural materials that combine wood fiber and resins. Working clockwise from the top left corner, here we see a few examples of engineered wood products including plywood, oriented strand board, or OSB, glulam, structural composite lumber, and I-joists. These products are likely the ones you build with every day. Here's a time lapse of a large project. This is what we're here for today, to examine how we can help builds go smoother, have fewer issues, and be completed with better structural quality. Like you frame a project, we're going to cover the basics from the ground up: walls, floors, roofs, and special details. The framer is critical to the quality and longevity of a structure. The responsibility of the design rests on the architect and the engineer of record, but you, the framer, has just as great a responsibility to assure that what is built matches what is in the plans. If you understand the principles involved, recognizing issues during the build becomes easier. You play a major role in ensuring that the load paths are accounted for in a structure, so let's look at some basic design principles regarding load paths. The load path is simply the route the forces take passing through the structure made up of its components and connections on the way to the ground. In the vertical load path, members above bear on members below, thereby transferring loads from above all the way to the foundation. Another type of load path is a lateral load path. The lateral or horizontal load path again shows the transfer of forces to the ground, but it's a little less intuitive. If the forces don't reach the foundation, there may be a failure, such as structural damage in a wind or an earthquake event. In a simple building, the forces begin at the wall in one direction and then transfer into the roof via the connections. The roof then transfers the force to the walls at each end of the structure. These walls become the shear walls and carry the load into the foundation, completing the load path. The engineer would analyze this same building in the opposite direction, since a wind or earthquake could impact the building in either direction. Now let's take a concept of tying our pieces together as we look at framing our structures from the ground up. Let's begin with the walls. The wall assembly is composed of vertical supporting members, wood studs, headers, plates, and sheathing. The lateral members, or wood structural panels, either plywood or OSB, withstand wind pressure and racking forces. The anchor bolts prevent the sill plate from sliding off the foundation, and the hold downs prevent overturning. How often do we see this at a site? How much capacity does the nut have without the washer? Or is the plate split already? The anchor bolt size and spacing should be determined by the engineer, but it's important to follow the drawings. Oftentimes this will be called out in a table on the structural sheets, but keep in mind this connection is keeping the wall from sliding off the foundation due to winds or earthquake forces. Large plate washers, when specified, are a great way to reinforce this connection and prevent the sill plate from failing in wood's weak direction, which is perpendicular to grain. Now, anchor bolts are not hold downs. Each has a specific and different task. Anchor bolts prevent sliding of the wall. Hold downs prevent overturning. Follow the engineer's plan for the hold down type and the locations. Hold downs are required to prevent the shear walls from overturning. There are a variety of different types of hold downs and manufacturers thereof, but the key is that they tie the wall down to the foundation or the wall below, engaging both the wall studs and sill plate, as shown, or the studs and rim board, as shown on the right. Strap hold downs, as shown here, can be effective, but they need to be installed correctly. The circle highlights where the strap is exposed. It should be embedded fully into the concrete. The strap on the far right is bent. This may have been due to construction traffic or an accident on site. Some straps and hold downs come pre-deflected in order to prevent a mishap, as shown in this photo. Another construction error is shown here. What do you suppose happened? If the bolt was not installed when the concrete was poured, the framer must post-install it with epoxy. This causes a loss of time, special inspection, and more material, which each increase the cost of construction. Now we discussed load paths. Here's an example of what appears to be too much load and not enough studs to support it. Note the multiple member just to the left, which may have been intended to transfer the loads from above. In this photo, a bearing wall had 3 floors above and was sitting just off of the beam that was meant to carry it. The same layout mistake was repeated on each floor above. The framing didn't miss by much, but this required major work to fix. Check load paths as you go up. Stacking alignment is always vital. Now the OSB in the previous photo was supporting loads well beyond what was intended. Let's briefly talk about some basics regarding engineered wood strength. As shown here, wood is strongest parallel to grain. Engineered wood products take advantage of that directional strength when the strands or veneers are placed at the time of manufacture. This diagram illustrates how veneers are layered in the production of plywood. The cross-lamination provides stability and stiffness. Many do not know that as with plywood, OSB is manufactured in layers with the grain of the strands running in perpendicular orientation to the adjacent layer to ensure dimensional stability and optimal structural properties. OSB is commonly produced in 3 or 4 layers, depending on the proprietary manufacturing process used at each mill. An I-joist utilizes OSB for the web material. The design of an I-joist puts material in the optimal locations for a light, strong product that outperforms conventional lumber joists. Besides having a built-in carrying handle, I-joists utilize over a third less wood fiber than lumber when spaced at 16 inches on center. Engineered wood products are successful due to the fact that they utilize wood efficiently while providing improved benefits. We will discuss the strength direction of panels and the features of an OSB I-joist web later on. Now let's talk panels and walls. The wood structural panel's main benefit is to keep the walls square. The more sheathing provided on the walls, the greater the building's ability to resist winds and earthquakes. It also provides other benefits, such as uninterrupted drainage plane, an air barrier, a continuous nail base for cladding materials. It also creates a stiffer wall, mitigating stucco cracking. What are the installation recommendations? The wall sheathing grade, thickness, and fastening will be called out in the plans. As a minimum, the panels should be fastened at the perimeter with 8-penny common nails at 6 inches on center, 12 inches on center in the field. Let's go again to some basics. Wood structural panels can be either plywood or OSB. In fact, the two are interchangeable provided you install the correct grade and thickness. The grade mark is stamped on each panel as shown in this example. Here you can see the grade is rated sheathing. This grade of panel is most common. When the buildings are larger, the loads increase, you may find structural 1 panels specified. We'll talk more about that in a moment. The thickness in this case is 15/32 category. Finally, the panels can be installed either horizontally as shown on the left side of the wall or vertically as shown on the right. Panels are typically 8 to 10 feet in length, the same as most wall heights. So many framers prefer to install the panels vertically. Also, if you install the panels horizontally, you will need to provide blocking along the unsupported edge, as shown here by the red arrow. When reviewing the plans, you may find 3 different types of shear walls. The first option is segmented, as shown in this photo. Each segment will have 2 hold downs. Perforated shear walls use sheathing on the entire wall, as shown here. A key benefit is that the hold downs are only required at the beginning and end of the wall, reducing the number of hold downs required. A third option is force transfer around opening shear walls, abbreviated FTAO. This also uses sheathing on the entire wall as shown here and requires hold downs at just the beginning and the end of the wall. The straps as shown in the photo transfer forces around the opening as the name implies. This additional strap allows the individual wall piers to be narrower than either segmented or perforated walls. APA has a free calculator on our webpage to make this design easier to provide. Again, as designed should be as built. Watch for small errors in materials shipped and check the fastening requirements carefully. So what is Structural 1? Structural 1 plywood is manufactured with Group 1 veneers in all plies, and those veneers have additional limitations on splits, knots, and knot holes. This gives the Structural 1 panels increased strength. OSB is also available in a Structural 1 performance-tested grade. A common question we receive is how do we nail into the framing when tight nail spacing is specified? Sometimes shear wall requirements can call for fasteners to be staggered, as shown here. This picture illustrates why staggering is recommended. When fasteners are aligned too close to one another, like in the first 2 examples, the nails begin to pry the wood apart and cause splitting. Minimal staggering, as shown on the right, prevents this splitting from occurring. Always take the time to check the framing prints for each level. The type of material or stud packs used often transition up through the floors, but always needs to be framed as designed or as an approved alternative. Remember, the loads are increasing from the top down, so the framing, sheathing, and fastening may increase as well. Why more fasteners? The number of fasteners directly affects the design values of a system. Wood structural panels can be designed to resist both shear and uplift, further minimizing the need for additional hardware. Running the sheathing from above the floor, or from the floor above to the floor below, as shown in this photo, demonstrates how wood structural panels can create a more direct load path. APA Report SR 101 gives the design values for combined shear and uplift. So what does that mean on site? The fastener pattern will be specifically designed and needs to be followed for the structure to meet design specifications. Lastly, as noted before, the wall sheathing also provides a nail base for the exterior cladding, alleviating the need to seek studs when attaching vinyl or brick ties. Now on to floors and floor framing. The floor framing is typically composed of wood structural panels supported by joists, beams, columns, and walls. The sheathing can be either plywood or OSB. Taking a moment to review a typical grade mark for the floor sheathing, you see the common grade is rated sturdy floor, which is a combination subfloor and underlayment. The subfloor provides the structural strength, and the underlayment provides impact resistance and a preferable base for the finished flooring. The engineer will also specify the thickness or span rating. In this case, we see 19/32 category and 20-inch on-center spacing. This means the floor supports can be spaced up to 20 inches on center. So what base values do we use in determining the span ratings for panel products? These maximum support spacings are based on live load values of 30 pounds per square foot for roofs and 100 pounds per square foot for floors. The dead load values for roofs and floors is 10 pounds per square foot. Live load deflection limitations are 1/360 for floors and 1/240 for roof applications. Notice the directional arrow notating the strength axis. Let's look at a quick example. In most cases, the strength axis is parallel to the long direction of the panel. In some limited cases, the strength axis may run parallel to the short dimension of the panel, as with some rated sheathing panels manufactured specifically for wall sheathing applications. It's not recommended to use panels in a simple span situation across only two framing members. If this happens, block both panel edges spanning the single framing space and fasten 6 inches on center, as with all nailable sheathing edges unless otherwise specified. Proper fastening is critical, and the order of nailing is important too. Are there shear wall or special fastening requirements on your project? Like the wall sheathing, the minimum recommended fastening is 8-penny common nails at 6 inches on center at the supported ends and 12 inches on center in the field. So on to some installation best practices. Make sure that the panel is put down on fresh adhesive. Don't be tempted to get way out ahead with the glue. And what is the purpose of a glued floor system? It eliminates squeaks and noise. How many of you do this on a regular basis? Why does this make for a better floor? APA recommends gluing not just the panels to the supports, but also the T&G edge as well. Now the panel should make contact with the framing members before the fastener is applied. There's no explanation required here. It does make it easy to see what type of fasteners are used on the job though. Overdriving fasteners can reduce performance and must be field checked to assure design intentions are carried through. Check as you go. Again, air gun settings are very important. Under or overdriven fasteners cost you time and money. Here's a chart from our publication TT12 that addresses overdriven fasteners. When it happens, here are the required fixes, but it's better to take the time to get the gun settings right and watch them as you go along. On projects with designed shear walls or diaphragms, fastening is critical, and these callbacks will cost you. Are the joists and trusses placed properly? Missing any extras under the wall lines above? Of course, an out-of-square truss can create uneven floors or wall plates above. Placement as designed is vital for proper load transfer through the levels. In this photo, one span of floor sheathing is spaced at over 24 inches. The floor will feel softer in that area due to the error in laying out of the joists. Now, was the alignment for plumbing noted on your layout? A quick overlay of bathrooms and fixtures on the floor joist layout can avoid big problems later. In this photo, I'm not sure that fire putty has been structurally rated yet. Now on to a brief look at the general hole cutting rules for I-joists. Because the shear forces are greatest near the bearing points of the I-joist, the web material may need to utilize the full design shear value of the joist. Generally, holes in the web material can be larger the further they are cut from the bearings of the I-joist. This is reflected in the hole charts shown in the APA Performance Rated I-joist Design Construction Guide, Z725, or the I-joist manufacturer's literature. It's always crucial that no part of the flanges be cut, notched, or in any way modified, as cutting the flanges will affect the published design moment of the product. It is recommended that a 1/8 inch section of web be left at the top and bottom of any opening. Remember, this is general guidance for one load configuration, which is uniform load. You may contact your I-joist manufacturer or utilize manufacturer-specific software to ensure the holes are properly spaced. When cutting multiple holes in I-joist webs, there are a couple of things to consider. First, the spacing between the holes should be a minimum of twice the size of the larger hole. However, if a group of holes within a circumscribed hole that meets the allowable hole size, then that's acceptable. Rectangular holes can be evaluated by circumscribing a circle around the corners of the rectangle. The size of the rectangular opening can be 3/4 of the diameter of that circumscribed circle. So for example, you could cut a 3-inch rectangular hole if a 4-inch hole was permitted. Also, when cutting rectangles, it is best to use a small radius at the corners of the rectangle so that those cuts do not create a sharp corner that may have a tendency to split further into the web material. Keep in mind these are general guidelines for cutting holes based on manufacturer's recommended specifications. What are your thoughts about the holes that have been cut into these I-joists? First, how about the location? Of course, these are too close to bearing. What do you think about the spacing of these holes? They do not appear to be spaced 2 times apart, so if we applied the hole grouping approach, the hole size would be the total of both holes plus the distance between the holes, which most certainly would violate the hole guidelines, being that close to bearing. Now, the bright side is that they stayed away from the flanges, so they've not been negatively impacted. Moving from joists to beams, laminated veneer lumber is comprised of veneers or plies of wood laminated together to create beams or columns similar to plywood. The veneers are oriented in a parallel direction to provide maximum strength in bending. LVL is a type of structural composite lumber which is available in longer lengths than conventional lumber. Another type of structural composite lumber is laminated strand lumber, or LSL, that incorporates wood strands as opposed to veneers and adhesives to create structural beam or vertical framing members, columns, or studs. Much of what we discuss with LVL beams also applies to LSL. However, because of the stranding, LSL often performs better in regard to shear. As such, you should consult with the LSL manufacturer regarding specific guidelines for cutting holes in LSL. Finally, glued laminated beams, or glue-lams, are manufactured by gluing nominal 2x lumber of varying widths, from 2.5 inches to 10 3/4 inches wide, into single beams. Like LVL, the wood grain runs parallel to the length of the beam. Again, engineering the wood in the products to take advantage of wood's strength properties to produce a strong, stable beam. Like I-joists, hole drilling is acceptable in both LVL and glue-lam. Cutting of holes in LVL is pretty straightforward. Holes can only be cut through the middle third of the height of the beam and the length of the beam. By cutting in this area, we are locating holes away from supports where we learned that shear is lower, and away from the beam edges to minimize impact on the allowable moment of the beam. The maximum hole size is 2 inches. Our APA Tech Note provides general recommendations, but for more detail, refer, of course, to the manufacturer's instructions. Here we have an example where you can field cut small holes in glue-lam. Glue-lam has more location flexibility than PSL and LVL. They are limited to the middle third depth and the center third of the span. The horizontal holes on a glue-lam are limited to 1/10 of the depth, or 1 lam, or 1.5 inches. The hole spacing equals 1 hole per 5 feet, and they must be spaced 8 diameters apart. So what is the depth of the notch in this LVL? Of course, a better question may be, why weren't the cripple studs shortened instead of notching the beam? When the bottom of the beam is notched, particularly at the end where the shear is greatest, the beam wants to pull away. Also note the overcuts in holes and notches contribute to reduced performance in any beam or member. We can't see the entire height of the beam, but if it isn't 20 inches or more in depth, this cut exceeds the 10% of depth rule in notching at the end of the LVL beam. This picture needs little explanation. How many different issues can you see here? There's excessive notching. We have holes too close together. And of course, the electrical looks pretty good too, by the way. Another field question we often get is concerning wood checking. Wood laminations in glue-lam are limited to 16% moisture content or less, which results in fewer seasoning checks than sawn timbers. These checks are noted by the presence of torn fibers and should not be confused with an adhesive failure or delamination, even though they occur near a glue line. Seasoning checks are seldom a structural concern, but they do impact the aesthetics of the beam. To minimize checking, install glue-lam in environments with consistent humidity levels and control the moisture content of the beams by protecting the wood from high moisture areas such as concrete or refrigeration, and thoroughly seal the beams on all 6 surfaces. If checking in a beam becomes a concern, you can refer to APA Technical Note F450, Owner's Guide to Understanding Checks in Glue Laminated Timber, which details a flow chart to evaluate checks in beams. A final note on glue laminated members. You can install preservative-treated or naturally durable materials which allow for an exterior application as shown in this photo. Treated beams and columns for exterior use are important for the life and long-term appearance of the structure. Moisture above 19% in wood can cause decay, therefore preservatives must be used. It's also important to note that there are specific treatments for given applications. Treated beams and columns may be stocked at local dealers and available in many areas. Now on to roof framing. It's typically composed of wood structural panels supported by trusses or rafters. The sheathing can be either plywood or OSB. Taking a moment to review a typical grade mark for roof sheathing, you see the common grade, again, is rated sheathing. The engineer will also specify the thickness or span rating. In this case, we see 15/32 category, 32 inches on center. This means the roof supports can be spaced up to 32 inches on center or 16 inches on center for floors. Wood structural panels are typically manufactured with the strength direction oriented in the long direction of the panel, so the panels should be installed with the long direction over at least 2 spans. So what are common roof framing mistakes? Let's begin by looking at the top plates. When APA observed tornado damage in Missouri, large sections of roofs were found blown off of homes. As you can see in the photo, these rafters were attached to the walls only with toenails. This connection was not sufficient to resist uplift forces, and failure occurred. Toenails are accepted in the code, but let's consider load path and how effective this connection is. It's important to understand that toenails only resist loads in certain directions, and thus are not recommended when the load application can be from several directions, as shown. Rather, a 3D connector, aka hurricane clips, are a very important construction component. They provide the connection between the wall and the rafter or truss. These clips should be installed per the manufacturer's recommendations and specified by the engineer of record. Some hardware manufacturers may allow the clip to be installed on the inside face of the wall. Here is the FEMA and APA recommended method of hurricane clip installation. This detail shows the hardware in line with the panel for a more direct load path. In the opposite direction of the trusses at the perimeter walls, we have gable ends. How will the roof load get down to the wall below? Wood structural panel sheathing over the gables is a great way to create a continuous load path. Note the bracing and strapping tying the gable back into the structure. Now onwards and upwards, let's talk about the roof sheathing. This is where everyone can see the workmanship from the road. This picture shows an example of buckling. We will cover buckling later on. The shingles can never cover this one up. The sheathing will follow the framing, so alignment is very important. This is a view looking down the ridge line of a roof section. The rafter peaks are out of alignment over 1 inch, making the roof deck look very wavy. Here's another common problem that we see. Our technical note R275 recommends a minimum 24-inch panel width in these situations. When less than a 24-inch panel is used, additional edge support is recommended. The figure to the right shows a doubling of the H-clips for additional support. The 2-inch wide strips shown in this instance, of course, are never recommended. So looking at this picture, what is wrong with this roof framing? There's actually more than one item wrong. We're missing an H-clip. We have, again, narrow pieces, wrong plywood orientation as well. So when the sheathing is turned 90 degrees, does it make a difference? Using APA Table 34 from our E30 publication, We show an allowable load of 100 pounds per square foot in this illustration. What if we turn the panel to run parallel with the framing underneath? We end up with a PSF value of 35 in this case. How we lay the panel makes a big difference. This is true for plywood and OSB alike. It also makes it very important that the right product is used for the spans and load conditions. That's why learning what the APA trademarks denote is important to those who install the product. Now we'll shift our focus to some special topics centered around on-site moisture management and shrinkage. This is unfortunately a common occurrence on construction sites. While we would encourage the removal of any precipitation on top of plywood or OSB structural panels as soon as possible, the panels are designed to withstand the level of moisture expected during a normal construction cycle. Cosmetic changes or even fungal growth may occur when the surface of the panels are exposed for extended periods. The bond classification of the panel does not relate to fungal decay resistance of the panel. Structural panels are manufactured at relatively low moisture contents. The first time that they are entirely exposed to moisture is upon their installation as floor, wall, or roof sheathing. As the sheathing panels increase in moisture content, they will increase in length and width. In order to restrain the panels in the flat plane of the system where they have been installed, it is absolutely necessary to space the panels at both end joist and edge joints by a minimum of 1/8 of an inch. Many panels are now undersized at the mill to accommodate this spacing and allows the panels to be installed on 16, 19/2, and 24-inch on-center spacings without requiring the framer to trim the panels in either both width or length. However, if panels measure a full 48-inch width or 96 inches in length, they must still be installed with 1/8 inch gaps at all panel edges. This may require some trimming to maintain your centers. Please see APA's installation guides for additional information. Exterior panels have bonds capable of withstanding repeated wetting and redrying or long-term exposure to weather, or even other conditions of similar severity. Exposure 1 panels are suitable for uses not involving long-term exposure to the weather. Panels classified as Exposure 1 are intended to resist the effects of moisture due to construction delays or other conditions of similar severity. Exposure 1 panels may also be used when exposure to the outdoors is on the underside only, such as at roof overhangs, although in these cases, appearance characteristics of the panel grade should also be considered. Exposure 1 panels are made with the same exterior adhesive used in exterior panels. However, because other panel compositional factors may affect bond performance, only exterior panels should be used for long-term exposure to the weather. Here's an example of the difference in the trademarks between Exposure 1 and exterior bond classifications. As a reminder, Exposure 1 panels will be fine for most applications as they will be covered with finished materials. Concrete form panels and siding are two more examples of exterior grade panels. Starting at the very bottom and working upwards, how's the grading at the foundation? If there is insufficient clearance to the wood portion of the structure, issues may arise as time passes, even during the construction process. Most exterior finished product manufacturers give a recommended minimum distance from the finished grade. Many jurisdictions enforce a code-mandated 6 inches slope on the first 10 feet away from the structure. Unless a product is rated for concrete contact, sidings, panels, and other finishes should not be in direct contact with the slab or foundation. A capillary break ensures that moisture does not wick into the products above. Here's what can go wrong when untreated wood rests on concrete. This is an example of capillary action. The OSB is touching the foundation below and is wicking moisture up into the product. In this case, there should be a gap between the panel and the concrete. Here's a detail that shows how to eliminate that issue utilizing flashing. So what happens to wood when it gets wet? Well, the APA recommends that wood structural panels, plywood or OSB, for floors, walls, and roofs be installed with that 8-inch space around the perimeter. If not, you run the risk of buckling as shown in the roof and wall sheathing here. This graphic helps us to better understand that a small expansion in the length or width of sheathing can result in a dramatic bow or buckling of the panel. This bowing may occur between the framing members and the fasteners, and the resulting out-of-plane movement can make waves, literally. Here's an example of wall buckling of the wood structural panels when what appears to be proper spacing techniques were used. You can see that there's significant buckling even with adequate gapping between the adjacent panels. So what happened here? Well, in this case, too many nails can be an issue. Improper acclimation of the panels may also have been a factor here. One of the most common errors we see happens on the roof. The H-clips keep the panel spaced, but the ends are overlooked. 1/8 of an inch minimum spacing on all 4 sides is essential during framing. APA has specific recommendations when using wood structural panels in special situations where there is an increased risk for buckling. These situations are when sheathing panels have their structural axis parallel to framing, when the required edge nailing is 4 inches on center or closer, the increased frequency of the fasteners can restrict the expansion of the panels, and where the panels may be exposed to high levels of moisture. So here are the recommendations for these special conditions. Allow panels to acclimate at the job site after the bundle is opened. Tack the panels in place before the edge fasteners are installed, then fasten with a nail spacing of 12 or 24 inches on center. After the panels have acclimated, fasten to specified on-center spacing. Also, as a reminder, fasteners should be installed 3/8 of an inch from the edges and ends of all panels. These recommendations do add some labor to the process, but oftentimes crews tack panels in place and then another crew follows to complete the final nailing per the design specs anyhow. Letting the panels get acclimated before installation and fastening takes some effort, but it's worth it. Straight from the bundle to the wall may result in movement as the panels reach equilibrium moisture content. Another moisture-related issue is mold. This was more than just improper ventilation. There was also warm, moist air from the building interior being dumped into the attic space in this location. And again, there was not enough ventilation to take care of the moisture. We've talked about the natural expansion of the panels with an increase in moisture content. When that is multiplied many times over on a structure like this, that expansion can literally move walls out of plumb and cause some major headaches. This is a detail for a temporary expansion joint used in the framing stage on buildings which are over 80 feet in length. If you've ever been on a project where the walls have pushed out due to expansion, this makes a lot of sense. After the building is dried in, nail the floor deck and fill the expansion joint with wood strip or non-shrink grout. Remember again to leave the 1/8 space at the panel ends and edges. Here is the provision detail for the roof framing on those large buildings. The fill-in panels can be installed as the roofing is applied. Remember to laterally brace the roof framing in the temporary roof openings and utilize protective barricades around the open areas for fall protection. Wood frame buildings are very economical to construct, and they can be very durable. In buildings designed In buildings designed to be 3, 4, or 5 stories, the effects of cumulative shrinkage can affect the building envelope, especially the exterior cladding. Even the driest wood can change shape due to moisture, no matter what you do to it, but you can learn what to expect. Wood shrinks perpendicular to grain. The shrinkage or expansion is directly proportional to changes in the moisture content. Framing up with wet materials and then closing in and conditioning the space may create issues with shrinkage as the structure dries out. This shrinkage must be accounted for in structures over 2 stories in height. In a wood frame structure, shrinkage occurs primarily in horizontal members such as wall plates and dimensional floor joists. Of note is the fact that engineered wood I-joists have less shrinkage than dimensional joists due to the composition of the fabricated products. When a wood frame structure is combined with a brick veneer, a concrete block elevator shaft, stair towers, or steel frame building elements, the cumulative effects of differential movement in a multi-story building must be accounted for. So here are a few tips with regards to minimizing the effects of shrinkage. Of course, the first tip is to keep the materials as dry as possible. Store materials properly and keep covers on your units. Store the units up off the ground and out of the mud. Load the floors as soon as possible. This weight helps in compressing the frame as it acclimates. Accommodations may need to be made for plumbing and other mechanical systems as the structure may shrink and settle, putting pressure on plumbing pipes, electrical components, and other installed mechanicals. Where steel columns are mixed into a large wood structure, it's very important to minimize shrinkage of the wood framing materials that surround them. Designers must take possible shrinkage into consideration when specifying dissimilar materials in a structural system. Now that concludes our portion on special topics. We've now discussed several steps that when followed can make a big difference in build quality. Doing the small things right, such as properly spacing panels, following fastening specifications, watching load paths, and controlling moisture on site will minimize errors and reduce callbacks. All these items lead to better build quality and improved profitability. At APA, we're here to help you with your projects. If you have questions or would like local on-site training, please contact our help desk or reach out to one of our engineered wood specialists. Within the Field Services Division, APA currently has 11 engineered wood specialists serving North America. Our goal is to provide assistance and support with all engineered wood products. Thank you for attending today. Framing large wood buildings is a growing market, and I hope this training will help when you see something that doesn't look quite right on your projects. Remember to pause and prevent in the present instead of framing and fixing in the future. Now at this time, I'm going to turn it back over to Karen, who's been monitoring questions throughout the session. If you have questions, please type them into the questions pane on the control panel on your screen. If you have any questions down the road or need help accessing the design resources we covered today, I've listed my contact information here.
Thank you, Darren. And just a reminder for the group that we will have this recorded session available on our website as well as the slides for download in the future. Some questions that came in, let's see. Number one, where can I find that temporary expansion joint detail for the large floors you shared?
That detail or that document is on our apawood.org website. The document number is U424, which is on temporary expansion joint details.
Okay, great. And another item, how can I fix the I-joist flange, like the photo that you showed with the sewer pipe that cut through the flange?
Now, I-joist repairs would be up to the particular manufacturer of the product. You should contact them for all repair issues or repair recommendations.
And the next one, you mentioned requirements for an 1/8-inch gap between panels, but how can panels expand if they've been glued or fastened to the supports?
The actual design and fastening requirements are actually taken into consideration with that expansion of the 1/8-inch gap. So there should be sufficient movement possible if the panels are fastened per recommendations. Now, we did show a case of overnailing where there were so many nails that it could not move. And again, we talk about acclimation and some of the installation details to prevent that on large structures.
Excellent. I agree, Darren. And I would also add in that we don't recommend gluing the roof or the wall sheathing either. So that would be a non-issue for wall and roof sheathing. How can I fix a buckled panel?
Now, a repair on a buckled panel can be difficult. It depends on the extent of the buckling. If there's slight buckling, a relief cut can be done at the edge or end of the panel. Sometimes fasteners would be removed for helping that movement or return to plane of the panel. If there's severe buckling and it has been there a while, then sometimes those panels will not return to plane and they will need to be replaced or blocking put in place to push the panel back to the plane.
How about in the session you talk about common nails? Can I use staples to fasten the sheathing?
Staples may be used. There are some jurisdictions that will not allow the use of staples. So you would need to check your local code and then also check with your fastener provider to see that your fasteners that you're using are a true equivalent. And then, of course, if you do use staples, there's typically an increased use because there's not a one-to-one ratio with nails or fasteners.
Great. I agree, Dan. That's a good add-in and a framer tip as far as tighter fastening is typically required, and to make sure the orientation of the staple is correct to engage the framing as well.
That's a good point.
And how about how do you fix walls that are out of plumb from expansion of panels if that temporary expansion joint was not provided for a large floor, as you shared earlier?
That, again, could be a tough one. It depends on the extent of the push out of the wall. Typically, it would come with pulling a panel or regaining the spacing. So I have seen where panels have been removed and the walls have been pulled back to plumb, and then the outer panels fastened or the panel gap refastened. That can be difficult, and it would depend case by case on what the procedure would be. We're always welcome to or happy to help. If you do have a situation come up like that, we can help with that.
Great. And in big buildings, would it be beneficial to use more hold-down connections in order to reduce the stress concentrations?
I think that is going to be, again, on a case-by-case basis. That's done typically by the engineer of record, and they should be utilizing enough to get the job done without having extras. But that would be something that would be per plan and would probably be beyond what we could recommend here generally.
Yeah, I would agree, Darren. And I would just point out that you shared the various shear wall approaches. So some of that concept is putting more of the work into the sheathing and reducing the reliance on hold-down connectors, which would be a point-by-point basis as opposed to spreading the load out along the wall. I think we have time for one more. If the plan calls for plywood, can I substitute OSB or vice versa?
Yes, we typically, if the thickness and the span rating is similar, plywood and OSB are interchangeable on projects. The only time where we recommend plywood over OSB would be in wet use applications, and those are special recommendations. But on a typical site, OSB and plywood are interchangeable.
Great. Thank you, Darren. Before we conclude, I would like to touch on 3 quick things related to a short survey, continuing education units, and upcoming webinars. We'd really appreciate receiving your feedback via the survey that you will receive shortly, so please take a minute and fill that out. Also, don't forget to download the AIA or ICC Certificate of Completion from the links in the follow-up email that will be sent to you an hour after the webinar ends. And finally, make sure that you're signed up to receive our APA Update newsletter so that you'll be notified of future webinars and updates to APA publications and standards. To receive it, all you need to do, starting from the home page of our website, is to click on Sign In the upper right-hand corner of the page. In the menu that drops down, simply select Register. From there, you will need to let us know what you'd specifically like to receive, which in this case is the APA Update newsletter. I should mention that if you have technical questions on any topic related to the use of engineered wood products, don't hesitate to contact the APA Help Desk at the address shown here. We also have APA field staff available to assist design professionals, builders, and code officials and framers, of course. Their individual contact information can be found on our APA website, www.apawood.org. Please feel free to reach out and take advantage of this resource. As mentioned earlier, a recording of today's webinar and answers to the questions that were asked will be posted at apawood.org in a week or two. And with that, I'd like to thank you for attending. Have a great day.